The second part of Chapter 4 focuses on stoichiometry and much of the math calculations involving chemical reactions. When we talk about stoichiometry, what we're referring to is the mole-to-mole ratios that we can write by balancing our equations using coefficients out in front. For example, if we look at this balanced chemical equation, this says that 2 moles of octane react with 25 moles of oxygen to produce 16 moles of carbon dioxide and 18 moles of water. Using any of the coefficients out in front of our species in this balanced chemical reaction, we can write mole-to-mole ratios from reactants to other reactants or reactants to products. So just a few examples of some ratios we can write. 2 moles of octane are equal to 16 moles of carbon dioxide. We could say 2 moles of octane always react with 25 moles of oxygen. We could also go from products back to reactants. For example, 18 moles of water are formed when 2 moles of octane react, or 16 moles of carbon dioxide are formed when 25 moles of oxygen react. There's many more mole ratios that can be written, and it's just going to depend upon what we're given in a problem and what we're asked to solve for. But anytime we have a balanced chemical equation, we can use those coefficients to write mole-to-mole conversion factors between substances. Let's first practice doing some basic stoichiometry calculations. We're given a balanced equation that says 3 moles of sodium hydroxide react with 1 mole of phosphoric acid to produce 1 mole of sodium phosphate and 3 moles of water. How many moles of sodium phosphate can be made from 0.240 moles of sodium hydroxide? So we want to start with our 0.240 moles of the sodium hydroxide, and we want to work our way over to the sodium phosphate, which is our unknown. We can use our mole-to-mole ratio between sodium hydroxide and sodium phosphate in our balanced chemical equation to do this. Starting with what we were given in the problem, 0.240 moles of sodium hydroxide. Then using our balanced chemical equation, we can write a mole-to-mole ratio. The balanced equation tells us that 3 moles of NaOH react to form 1 mole of sodium phosphate, Na3PO4. This is the important new step that we need to write using stoichiometry. And since we're actually just trying to find moles, that's going to be the end of our calculation. So if we take 0.240 and divide by 3, that should give us our answer, or 0.08 moles of sodium phosphate. Part B says, if 0.350 moles of water are produced, how many moles of phosphoric acid must have reacted? So this time we're starting with a product. We're being told that we made 0.350 moles of water, and we're going to work backwards from our water to the H3PO4, which is phosphoric acid. We're going to use our coefficients out in front of phosphoric acid and in front of water this time. Starting with what we were told, 0.350 moles of water, and then writing our mole-to-mole ratio, 3 moles of water are produced when every 1 mole of H3PO4 reacts. So if we take our 0.350 and divide by 3, that'll give us 0.117 moles of the phosphoric acid that must have reacted. This is a rather simple example where everything that we're starting with and ending with is in moles. So we're just focusing on writing those new relationships between reactants and products or products and reactants using our balanced chemical equation. Usually the calculations in your homework problems will be a little bit more involved. If you go out into the lab, we don't mass things in moles, we mass them in units of grams. So the pattern will usually look something like this. We'll start with the grams of some substance, whether it's a reactant or product. Then we'll have to use or calculate the molar mass of that substance to convert into units of moles. Once we're in moles, then we can use our balanced chemical equation, or balance it if we need to, in order to convert from moles of one substance into moles of another substance. Then often the answer will be asked for in units of grams, so we'll have to calculate and use a second molar mass of substance number 2 in order to convert it from moles into grams. So our outline of what we're going to do would be grams to moles, and then moles to moles using the chemical equation, and then moles back to grams of something else. Let's try an example. A chemistry student needs to prepare 150 grams of calcium oxide according to the following equation. How many grams of calcium carbonate should be used? So we're told that we want to prepare 150 grams of calcium oxide, and we're given our balanced chemical equation. You should always check the equation at first to make sure it is balanced in case you need to balance it yourself. In this chemical equation, since it's balanced, everything reacts in a 1:1:1 ratio. We're starting with 150 grams of the calcium oxide and figuring out how much calcium carbonate we would need to produce that. Looking at our roadmap, we're starting with our mass of calcium oxide. We would need to calculate the molar mass of calcium oxide in order to convert from grams to moles. Our molar mass of calcium oxide should be about 56 grams per mole. Once we're in moles of calcium oxide, then we can use our balanced chemical equation. We can see that the calcium oxide and the calcium carbonate are in a 1:1 mole ratio. That allows us to move into moles of calcium carbonate. From there, we'll need our molar mass of the calcium carbonate in order to convert to grams of calcium carbonate. So we would have to calculate this. Our molar mass of calcium carbonate should be calculated to be about 100 grams per mole. And that'll get us into the correct units of our final answer. So we want to start with the number we were given in the problem, which is our 150 grams of calcium oxide. Using our molar mass, we can convert to moles, 56 grams of calcium oxide in every mole. Then looking at our balanced chemical equation, our calcium oxide is in a 1:1 relationship with the calcium carbonate. That means that every 1 mole of calcium oxide that reacts, or that is produced, since it's a product, it must have came from 1 mole of calcium carbonate. If we were to stop now, our grams of calcium oxide cancel, our moles of calcium oxide cancel, and we're in moles of calcium carbonate. Next, we need to use the molar mass of the calcium carbonate in order to convert back to grams. 1 mole of calcium carbonate is about 100 grams. Lastly, now our moles of calcium carbonate cancel, and we're in units of grams. We should get about 268 grams of our calcium carbonate that would be required to make 150 grams of calcium oxide. This is a typical setup for most stoichiometry problems where you're only given one amount of either a reactant or a product. Let's try another example. A welding operation requires at least 86 grams of iron each time a weld is made. What are the minimum masses in grams of iron 3 oxide and aluminum that are required for each weld? So in this example, we're starting with the mass of one of our products. We're told that we need 86 grams of iron. So our goal is going to be to start with our iron and work backwards and figure out how much iron 3 oxide would be required to make 86 grams of iron. And in a separate calculation, work from the iron back to the aluminum and figure out how much aluminum would be required to make that amount. So before we do anything, we want to check our equation and make sure it's balanced. In this example, there's 2 aluminum atoms on the right and only 1 on the left. So we're going to put a 2 out in front of our aluminum. On the left-hand side, there's 2 iron atoms and only 1 iron. So we're going to put a 2 out in front of our iron. And there's 3 oxygens on the left and the right-hand side. So now everything is balanced. We're going to have to set up 2 separate calculations, one to calculate the amount of iron 3 oxide and the other to calculate the amount of aluminum. Let's start with the iron 3 oxide. We need to start with what we are given in the problem, which is our 86 grams of iron. And in order to use our balanced equation, the first thing we have to do is convert our grams of iron into moles of iron. In looking at the periodic table, to get the atomic mass of iron, 1 mole of iron is about 55.85 grams. Now we're in moles of iron, and we can use our balanced chemical equation in order to convert from moles of iron into moles of iron 3 oxide. According to the reaction, 1 mole of iron 3 oxide reacts to form 2 moles of iron. Our 2 moles of iron are going to need to go into the denominator, so it'll cancel, and our 1 mole of iron 3 oxide will go into the numerator. We can see that our grams of iron are going to cancel. Now our moles of iron will cancel. We are in moles of iron 3 oxide at the moment. And lastly, we're going to convert our 1 mole of iron 3 oxide into grams by calculating the molar mass. When you calculate the molar mass of iron 3 oxide, you should get about 160 grams per mole. So now your moles of iron 3 oxide can cancel, and the mass needed in moles, the mass needed in grams should come out to be about 123 grams of Fe2O3. That answers the first part of our question. Now for part 2, you have a couple options. You could start with the 86 grams of iron, or you could actually start with the 123 grams of iron 3 oxide that you just calculated and go from iron 3 oxide to aluminum. Either way should give you the same answer. I'm going to start with the 86 grams of iron again. 86 grams of iron, and we're going to need to convert that into moles just like we did in the first setup. 1 mole of iron is about 55.85 grams. Now looking at our balanced chemical equation, this time we want to go from iron to aluminum. We can see that 2 moles of iron are produced for every 2 moles of aluminum that react. From our moles of aluminum, we want to convert to grams. Using the periodic table, we can see that the atomic mass for 1 mole of aluminum is 26.9 grams. Our grams of iron cancel, our moles of iron cancel, moles of aluminum cancel, and we have our mass of aluminum in grams, which should come out to be about 41.6 grams of aluminum. In all of our previous examples, we were only given the mass of either one reactant or given the mass of one product. Even though it didn't state this, we were assuming that the mass of the other reactant was in excess, so that all of the mass of the one that we were given could react completely. Usually this is not the case in the real world. When we look at a balanced chemical equation, it's telling us exactly how to mix together the reactants in the perfect proportions to get certain amount of products. They're often called stoichiometric amounts or stoichiometric coefficients. But usually we're not using that true exact amount of our reactants needed. More often than not, we're going to have one reactant that's present in excess, where we have some left over, and one reactant that limits the amount of product that can really be formed. This brings us to the second type of stoichiometry problem we're going to look at, called a limiting reactant type. First, we're going to look at a couple definitions. A limiting reactant in a chemical reaction will be the reactant that actually limits the amount of product that can be formed. The reaction will stop when all of the limiting reactant is consumed. We can't make more product than the limiting reactant will allow us to. Another reactant will be defined as the excess reactant. This will be the reactant that remains after the chemical reaction is over and the limiting reactant is consumed completely. The excess reactant will not limit the amount of product that can form because it won't all be used up. Some of it will be left over at the end. An analogy for limiting reactants is thinking about making sandwiches. If we were to write a recipe for making a grilled cheese sandwich, the recipe would be a lot like our balanced chemical equation. We would need 2 slices of bread for every 1 slice of cheese, and with that we could make 1 cheese sandwich. If we had the perfect stoichiometric amounts, we would have perfect 2 slices of bread, perfect 1 slice of cheese, and we could make perfectly 1 sandwich. But let's imagine we have different amounts than are told to us based upon the stoichiometric coefficients. Let's say now that we have 6 slices of bread and we have 2 slices of cheese. We still have to react our bread and our cheese according to our recipe, which is our balanced chemical equation. If we were to think about how many sandwiches could we make, first we can make 1 sandwich. We'll use up 2 slices of bread and 1 slice of cheese in order to do so. Next, we could make another cheese sandwich. We would use up another 2 slices of bread and another slice of cheese in order to make a second sandwich. At this point, we're done. We can't make any more cheese sandwiches. We ran out of cheese. Therefore, the cheese limited the amount of sandwiches we could make, even though there is still bread left over. Therefore, the limiting reactant in this example would be our cheese. And our excess reactant, we can see is the 2 slices of bread that is remaining after the reaction is over. So the excess reactant would be the bread. It remained unconsumed at the end of the reaction, or at the end of making the grilled cheese sandwiches. This is exactly how it works in a chemical reaction. Usually there's 2 amounts of reactants that are mixed together. One reactant will limit the amount of product that can be made, and the other one will not get used completely, and therefore it'll be the excess reactant. Now let's look at an example involving some chemistry. This reaction is the synthesis of ammonia. It says that for every 1 mole of nitrogen, it reacts with 3 moles of hydrogen to always produce 2 moles of ammonia, or NH3. If we look at our amount of reactants that we're starting with, everything on the left-hand side of the arrow, we can see that we're starting with 3 moles of nitrogen, represented by the green spheres, since nitrogen is a diatomic molecule. And we're starting with 6 moles of hydrogen, H2, represented by the gold spheres. Hydrogen is also a diatomic molecule. And initially, we have 0 moles of ammonia on the left-hand side, because we haven't formed any product yet. If we group together our nitrogen and our hydrogen according to our balanced chemical equation, we can see what we need to form our ammonia. For every 1 mole of nitrogen, it combines with 3 moles of hydrogen. So we have 1 mole of nitrogen combining with 3 moles of hydrogen, and that forms 2 moles of our ammonia. So that would form 2 of our ammonia molecules on the right. And on our left-hand side, we can group together 1 more mole of nitrogen with 3 more moles of hydrogen, it looks like. So 1 more mole of nitrogen with those 3 moles of hydrogen, and that'll form 2 more moles of our ammonia on the product side. So now after the reaction, we were able to form in total 4 moles of NH3, 1, 2, 3, 4. And we were left over with this 1 mole of NH2 that could not react. It didn't have anybody to react with, so it is excess at the end of the reaction. It still remains. That's where our 1 mole N2 after comes from. So therefore, if we're determining who limited our reaction and who was in excess, we ran out of hydrogen first. So hydrogen would be defined as our limiting reactant, and our nitrogen remained unreacted. Some of it did, therefore it was our excess reactant. It's going to be important when we start looking at the math side of limiting reactants that we can determine who our limiting reactant is and who our excess reactant is. So now let's expand upon our last example with ammonia synthesis and put some numbers to it. We still have the same balanced chemical equation where 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. We're going to answer the following questions on 3 separate slides. A, given 9 moles of hydrogen and 4 moles of nitrogen, how many moles of ammonia can actually be formed? So now notice this is different from our previous examples because we're being told the amounts of 2 things. We're being told the amount of hydrogen and the amount of nitrogen. In part B, how many moles of nitrogen are required to react completely with 9 moles of hydrogen? And then C, how many moles of excess reactant are left over after the reaction? To keep this example straightforward, we're doing everything in moles and not introducing our conversion from moles to grams just yet. Let's start with A on the next slide. Given 9 moles of hydrogen, so we're going to put our 9 moles of hydrogen below it, and 4 moles of nitrogen, so we'll put our 4 moles of nitrogen below nitrogen, we want to know how many moles of NH3 can be formed. In order to answer this, we're going to have to figure out how much ammonia can be formed if all of our hydrogen reacts by starting with our 9 moles of hydrogen, and we're going to have to figure out how much ammonia can be formed if all of our nitrogen reacts by starting with our 4 moles of nitrogen. From there, we can do an analysis of both of our final amounts of ammonia that's formed and see how much would really be formed. This will also tell us who our limiting reactant is and who our excess reactant is. You can't just simply look at the amount that you're starting with. Just because 9 is a larger number than 4 doesn't tell you anything about who the limiting and who the excess reactant is. We have to use the balanced chemical equation of 1 to 3 to 2. So let's start with our 9 moles of hydrogen. When we have 9 moles of H2, according to the balanced equation, 3 moles of hydrogen react to form 2 moles of ammonia. Our 3 moles of hydrogen will have to go in the denominator, and our 2 moles of NH3 will have to go in the numerator. This is because we want our moles of hydrogen to cancel, and we want to know how much ammonia we form. That will give us 6 moles of an NH3 product. And this is if all of our hydrogen were to react, we would form 6 moles of ammonia. If all of our nitrogen reacts, so we start with our 4 moles of N2, and we look at our balanced chemical equation, 1 mole of nitrogen reacts to form 2 moles of ammonia. Our nitrogen will go in the denominator. Our ammonia will once again go in the numerator. Our moles of nitrogen cancel, so we're in moles of NH3, and that'll give us 8 moles of ammonia if all of our nitrogen were to react. Once we have the 2 amounts of product that can be possibly formed, we need to compare them. We can only form the lesser amount of product because we'll run out of one of the reactants before the other. Therefore, we're not really going to form 8 moles of NH3. We'll really form 6 moles of NH3 because this is our lesser amount. So that tells us that the lesser amount, the reactant that was reacting in order to give us that amount, which in this case was the hydrogen, that must be our limiting reactant. The one that gave us the greater amount of product, which was the nitrogen, that must be our excess reactant. So this set of 2 calculations tells us how much product we actually were able to form, which was the 6 moles because it was smaller than 8 moles, and the reactant that gave us the lesser amount of product is our limiting reactant we'll run out of first. reactant that gave us the greater amount of product that we really couldn't form all of would have to be our excess reactant, which is the nitrogen in this case. So it's important to make note of who your limiting reactant is and who your excess reactant is. Let's go on to part B, now that we know that hydrogen is limiting and nitrogen is excess. Part B says how many moles of nitrogen are required to react completely with the 9 moles of hydrogen. We just figured out that hydrogen was our limiting reactant and nitrogen was our excess reactant. Initially, we started with 4 moles of our nitrogen, but we know that not all of them are going to react. There's going to be some left over. We want to figure out how much nitrogen is actually going to react in this problem with all 9 moles of our H2. This time we're going to start with our 9 moles of hydrogen, but we're going to work to our other reactant, which is our nitrogen, and find out how much will react. Starting with our 9 moles of hydrogen, since we're already in moles, we can directly look at our balanced chemical equation. 3 moles of hydrogen will always react with 1 mole of nitrogen. And our hydrogen is in the denominator, so it cancels. Our mole of nitrogen is in the numerator, and that means that 3 moles of nitrogen will react. As we expected, we got a number that was less than 4 because we knew that nitrogen was our excess reactant. So really we only needed 3 moles of nitrogen to react completely with the 9 moles of hydrogen that we had. The last part, we want to know how many moles of excess reactant will remain after the reaction is over. We know that nitrogen is our excess reactant. And in the previous slide, we just calculated that 3 moles of our nitrogen will actually react with all of the hydrogen, since the hydrogen was our limiting reactant in this example. Therefore, if we take the difference between the moles that we are starting with initially, we had 4 moles initially, and subtract off the amount that reacts, we can figure out how much will remain or be left over after the reaction. So we started with 4 moles of nitrogen initially, subtract our 3 moles of nitrogen that reacts, and what we're left with then is 1 mole of nitrogen that remains. That's how much will be left over as our excess reactant when this chemical reaction is complete. Now let's try a limiting reactant example where we add in our gram to mole conversions and follow the entire sequence of steps. You are given in the upper right corner the molar masses of the substances in this problem, so you don't have to calculate them. But remember, if you're not given them, you're going to have to calculate the molar masses yourself. Let's get started. What mass of calcium sulfate is produced according to the given equation when 5 grams of each reactant are combined? So we know that we're combining 5 grams of calcium fluoride with 5 grams of sulfuric acid. The products of this reaction are calcium sulfate and hydrogen fluoride. In this example, we're interested in only the calcium sulfate. We're going to take our 5 grams of sulfuric acid and figure out how much calcium sulfate could be formed if all the sulfuric acid reacts. And our 5 grams of calcium fluoride, figure out how much calcium sulfate will be formed if all of the calcium fluoride reacts. So this is different from our previous ones, remember, because now we're given the mass of 2 different things in the problem. We're starting with the mass of both of our reactants. So this is going to be a limiting reactant example. We can choose one and just start there. Let's start with the calcium fluoride. 5 grams of calcium fluoride. And in order to use our balanced equation, we're going to have to convert our grams into moles. And we have the molar mass in the upper right corner, 78 grams is 1 mole of calcium fluoride. From our balanced chemical equation, we can see that the calcium fluoride reacts in a 1-to-1 ratio to form our calcium sulfate. So for every 1 mole of CaF2 that reacts, we produce 1 mole of CaSO4. Lastly, using the molar mass of calcium sulfate, 1 mole of calcium sulfate in the denominator is about 136 grams. Our grams of calcium fluoride cancel, our moles of calcium fluoride cancel, moles of calcium sulfate cancel, and our units will be grams of calcium sulfate. Remember, this might not be our final answer just yet, but so far we know that 8.72 grams of calcium sulfate can be formed if all of our calcium fluoride reacts. Next, we'll do an example, and we'll start with our mass of sulfuric acid, H2SO4. If all 5 grams of H2SO4 react, let's figure out how much of our calcium sulfate can be formed. First, we have to convert our grams of sulfuric acid to moles. 1 mole H2SO4 is 98 grams, making sure to put our grams in the denominator and our moles in the numerator. Looking at our balanced equation, the sulfuric acid reacts 1-to-1 to form the calcium sulfate. 1 mole of H2SO4 forms 1 mole of CaSO4. And then lastly, we use the same molar mass for calcium sulfate to convert back to grams. 136 grams per every 1 mole of calcium sulfate. We check that our grams of H2SO4 cancel, our moles of H2SO4, our moles of calcium sulfate, and we have units of grams. Our mass of calcium sulfate formed if all the sulfuric acid reacts is 6.94 grams of our calcium sulfate. So now we do our analysis. If all calcium fluoride reacts, we can form 8.7 grams. But if all sulfuric acid reacts, we can form only 6.9 grams. The amount that forms will be the lesser of the two amounts. So we can form 6.94 grams really of our calcium sulfate product. Since that's our lesser amount, that tells us who our limiting reactant is and who our excess reactant is. The H2SO4 limited the production of product that we could form. Therefore, sulfuric acid is our limiting reactant. The calcium fluoride gave us a greater amount that we really couldn't form. This is going to be our excess reactant because we will have some of it left over after the reaction is finished. This next example is a little bit of a twist on our limiting reactant type problem. We're given a balanced equation. 3 moles of potassium hydroxide react with 1 mole of phosphoric acid to form 1 mole of potassium phosphate and 3 moles of water. We're also given the molar masses of our substances in our equation in the upper right corner. And we want to determine the starting mass of each reactant if 55.7 grams of potassium phosphate are produced and 89.8 grams of phosphoric acid remain unreacted. Let's just focus in on our grams of potassium phosphate right now. So since that's one of our products, if we list that below, 55.7 grams of potassium phosphate, we can start there and work backwards to figure out how much phosphoric acid reacted. We can also start at our mass of potassium phosphate to figure out how much of our other reactant, which is our potassium hydroxide, how much of that reacted as well. This problem tells us a little bit about our limiting and our excess reactant in the words. It says 89.8 grams of the phosphoric acid remain unreacted. If there's unreacted phosphoric acid at the end, that must mean that the H3PO4 is our excess reactant. Therefore, the potassium hydroxide must have been our limiting reactant. We're going to start with our mass of potassium phosphate produced. In this example, we have 55.7 grams potassium phosphate. In order to use our balanced equation, we need to convert our mass in grams into moles. 1 mole of potassium phosphate is 212.27 grams. And if we just start with our mass of phosphoric acid that we're determining, we can use our mole to mole ratio there. 1 mole of K3PO4 reacted from 1 mole of H3PO4 from the balanced chemical equation. And then using our molar mass of phosphoric acid, we can go back to grams. 1 mole H3PO4 is 97.99 grams. Before we do anything, we should check our grams of K3PO4 cancel, our moles of K3PO4 cancel, moles of H3PO4 cancel, and we have our mass. We should get 25.7 grams of our phosphoric acid that reacted. That's not necessarily our answer because the question asked us to determine the starting masses, but we'll make note of that for now. Going back to our other reactant, the potassium hydroxide, we could either start with our 25.7 grams of phosphoric acid, or we can start with our mass of potassium phosphate. Just to stay consistent, let's start with our 55.7 grams of K3PO4. Using the molar mass of 212.27 grams to convert into moles of K3PO4. Now looking at our balanced equation, every 1 mole of potassium phosphate that's formed came from 3 moles of potassium hydroxide, according to our equation. And then converting our moles of KOH into grams, 1 mole of potassium hydroxide is 56.11 grams. This gives us 44.2 grams of KOH that reacted. Since the potassium hydroxide was our limiting reactant, all of it got used up. Therefore, all of it that reacted is what we started with. So that is the correct amount of our starting mass of potassium hydroxide. But for our phosphoric acid, we know how much remained at the end, 89.8 grams. And if we add the amount that reacted that we calculated, 25.7 grams, that'll give us our amount that we started with, which should be about 115.5 grams of the phosphoric acid initially.